Right. Thanks very much. I know it's right before lunch, but I promise this one's going to be exciting. This is kind of a project I've been working on for a little while about sort of just fun with caches and side channel stuff. And I've been kind of taking my time with it. And, what happens when you do that is, it turns out other people have the same great idea that you do. And so I actually found out fairly recently that a team out of Tel Aviv University and the University of Adelaide came up with a very similar technique that what I'm presenting here, but they had a much better name for it than I did. Their paper is under submission. I'm in contact with them. We're working together now. So if you like what you see here, keep an eye out for their paper. They're a better writer than I am. All right, so today I'm going to be talking about cache side channels, but kind of a different aspect than is usually presented at these type of things. If we think about basically any cache side channel at a 10,000 foot level, it has three general phases. So first off, there's a setup phase where the attacker is going to put some parts of the cache into a known state, either evicting some lines or bringing in some lines. You're then going to let the victim code run, which is going to perturb the cache in some way. And then there's this recovery phase where you're trying to figure out what happened to the cache. And for this talk, we're going to be focusing on that recovery phase exclusively, which also means that the stuff here kind of applies to pretty much any cache side channel tech you want to do. So when it comes to the recovery phase, I call this reading the signal, because the idea is you've got a cache line that may be present or not present, and you want to figure out what the state is. And typically, this is pretty straightforward. You use a high-precision timer, which in x86, we like the CPU timestamp counter. And we just time how long it takes to access the line. If the line's in the cache, CPU gets the data quickly. If the line's not in the cache, it takes a while going out to DRAM. And then what that means, the state of that cache line, that's going to be dependent on your specific attack. So if you're doing a flush and reload attack, you're looking to see if a line is present. If you're doing a prime and probe, you're looking to see a line is not present. And then you'll interpret that in the context of your overall attack. So, some questions to pose. Do we really need a high-precision timer to check the status of a cache line? Or do we at least need a somewhat high-precision timer? And then, my favorite is, if we've got a bunch of cache lines, do we actually have to check each of them in order to determine their state? And of course, the answer to all these is no, because that's why I'm up here talking. So before I go into exactly how we're going to do this, let me first start with some basic primitives. And we're going to look at the code here, which is very simple code, but we're going to look at it under a very specific set of circumstances. So in particular, we've got these two cache lines, and we're going to assume that the state of the first cache line A is unknown, but we know the cache line B is not present. We also know that the memory at address A is 0, meaning that this branch is not going to be taken. However, we're going to assume that the CPU mispredicts the branch and thinks that it is taken. And the key insight behind this work is the fact that the amount of time that it takes the CPU to correct itself when it mispredicted the branch depends on how long it took to access that cache line A. If it took a short amount of time, because the line was present, then it is not going to have time to fetch cache line B. If initially the cache line was not present, speculation goes on for a long time, we do fetch cache line B. And the result here is that the state of cache line B is set to the inverse of the state of cache line A, even though we didn't actually have to do a timing measurement on cache line A. So that's the basic thing, then we're going to go from there. So first off, how do we build this reliably? And I'm a hardware guy, so I tend to go towards assembly, and you get to do some tricks with assembly that you might not get to do in C. And this is one of my favorite, which is a forced misprediction. So the way this code works, and don't worry if you're not big into x86 assembly, is that we are going to do a call instruction to label 3, and then we're going to overwrite the return address on the stack. And this takes advantage of the fact that in pretty much every modern CPU, regardless of vendor, return instructions are always predicted to where your previous call instruction was. And so we're going to leverage that. So we're going to overwrite the return address on the stack to be label 4, So we will, in fact, architecturally go to label 4, but when we speculate, we actually are going to go back up here to label 2 and execute the instructions there. The great thing is that this works every single time. The CPU never learns that this thing is always getting mispredicted, so it's great. All right, so let's look at the full code for the inverter. We're going to use that gadget we just showed and overwrite that return address. And then we are going to read cache line A, which we're going to assume is an RSI. We take the result of that, which we said was 0. The values in the cache lines don't really matter for this talk. We're going to add that value to the address that's at the top of the stack. Doesn't change it, but it creates a data dependency. When that return instruction misspeculates, we're going to go up to the red code here, which is in red because it's never actually executed for real. The first thing is there are some delay ops in here, and this gives the CPU pipeline time to correct itself if that initial cache line A was present. If that cache line was not present, the return instruction is taking a long time to execute. We're going to eventually get to this load here, and we'll read cache line B. Another way of looking at it is with this grossly oversimplified pipeline diagram. So the top case is where the cache line A was present. And as you see, the ops are able to execute back to back. As soon as the return instruction executes, we flush the pipeline and we never get to the fetch of instruction B. In the bottom case, as you notice, there is a data dependency, so the load takes a long time, the add has to wait, the return has to wait, but the fetch of the delay ops and cache line B is independent of that, and so we take advantage of the out-of-order execution of the CPU, and it's able to fetch cache line B. So hopefully that's making sense. Good. All right. So now I'm going to take that same code, I'm going to add one more instruction, which is what's shown in green right here. And this time we got 2 cache lines. So we got the one in RSI, we got one in RDX. And notice that there's a dependency here. So we are taking the result of the second cache line and we are adding it to the result we got from the first. If both of these cache lines are not present, then the speculation is going to go on for a while. We bring cache line B. The same happens if either one of the cache lines is not present, because we got to wait for both. If they're both present, then we execute the return quickly, and we don't have cache line B. So we've kind of just created a NAND gate. So that's kind of fun. So what else can we do? Quite a number of things. One of the gadgets that we're going to use quite a bit in this talk is what I call a replicator. This is basically an inverter with multiple outputs. So instead of having one cache line B, we could have B, C, and D, etc. So this is great for copying the state of cache lines. You can build a NOR gadget. It's a little bit trickier. I would encourage anyone who's interested to try, and I'm available for questions. You can also kind of trivially just expand these out to more inputs, right? We just showed a 2-input NAND. You can do a 4-input NAND, whatever you need to do. You may ask about why I'm always assuming things have a value of 0. That's because when you're doing a cache side channel, you control the data, right? You're just looking to see what the victim has done to the cache, whether they have, touched cache lines or evicted cache lines. So just to simplify everything, we can assume that everything has a value of 0. All right, so let's talk about amplification. So the problem statement here is we've got this one cache line. We want to know the state of it, but we don't have a high precision timer. So how are we going to figure it out? And in all the techniques I'm going to show, the idea is that we'll start with that cache line. We're going to run some code, and we're going to do a timing measurement. And if the cache line was present, we're going to get one result. If it was not present, we get a second result. We want the difference to be as big as possible. In the kind of naive, straightforward code I showed before, we have a signal strength of a little over 200 cycles. Not great. So the first building block here is the single-stage amplifier. And this has 2 parts. the first is that replicator gadget I mentioned earlier, where we're going to take the first cache line, we're going to make a bunch of copies of the inverse of that cache line. And because of the way that works, those are all going to be fetched in parallel. And then we're going to do a timing measurement where we access all of them sequentially. And we do this by just exploiting data dependencies, right? The processor can fetch things out of order if they're independent. But if we force the result of one to be dependent on the previous result, then we can force it to execute sequentially. So in the part that I did for testing on this, which was an AMD part, I could actually fetch about 23 cache lines during speculation based on a single cache line. For the picture here, I just shown 3, for example. So the idea here is that we're going to run this gadget, and we're going to be in one of these two conditions, right? Either B, C, and D are going to be all present, or they're going to be all not present. And when we do our timing measurement, we've now increased our signal strength to about 700 cycles. So not bad. So how do we go beyond this? Well, the naive thing, and the thing that I first tried, was to just like repeat it, like to bring in 23 cache lines, then each of those brings in another 23 cache lines. Problem is you run out of cache really fast, and there's a limit, and then you run into system noise, and it doesn't really work well. So the better technique is this thing that I call a self-reinforcing amplifier. And in this case, we're going to do that single-stage amplifier, but we're going to keep one cache line behind. So we're going to bring in 23. We're going to time the access, or I should say, actually, we're just going to access 22 because we're timing the whole thing. We're going to access 22 of them, and then we're going to take the one that's left, we're going to invert it, and we're going to restore the original signal. And this is important because this stuff is kind of like Schrodinger's cat, right? Anytime that you use it, you bring the thing in, and you can't use it anymore. So we create 23 copies, we use one to restore it, access the rest. And we repeat this a lot. We can repeat it up to a point, and then the data kind of gets noisier. Every time that we do this, there is a risk of system interrupts, other kinds of system noise, and so that's why the results kind of trail off. But, we can do about 700,000. That's pretty good. So if we do 700,000 and we run it 1,000 times, this is the results that I saw. And so what I'm showing here is signal strength. So again, that's the difference between the timing when the cache line was present versus not present. In some cases, it's over a second. So this code ran for a second of wall clock time difference based on that one initial cache line. And so even if you have a pretty bad timer, you can still figure out what the state of that cache line was. With a 500 millisecond timer, you get it right about 50% of the time. You get it wrong about 10% of the time. If you have a slightly better timer, though, the results are much better. If we don't go quite as aggressive and we go with like 100,000 amplifier, meaning we repeated that loop 100,000 times, we get a average signal strength about 180 milliseconds. With a 100 millisecond timer, that's over an 80% chance of recovery. 10 millisecond timer, 95% chance. That's over a 2 million amplification from the base signal. So that's pretty good. We don't need a good timer to do a cache side channel attack. All right, now what else can we do? This is the fun part. So I'm going to present 2 problems here. First one is a binary search. Right? We have an array of cache lines. One of them is present. We don't know which. We want to find which one is present, doing the fewest timing measurements possible. In real life, this would be a case where perhaps you're doing a flush and reload attack, and the victim has indexed some array and has brought in a cache line that's dependent on a secret value. And maybe there's 64 different values. So we want to do a binary search, but we have this problem of losing state, right? Every time we touch the cache line, we bring it in. So the way we're going to do this is in 3 steps. We're going to start with the signal array at the bottom here, and in this picture I'm showing 8 cache lines. One of those is present. We're going to create this working array with a replicator. So we're going to take each line, we're going to create 2 copies of the inverse of that. So in this array, we've got 16 lines, 2 of them are not present. We're then going to use our NAND gadget to check the status of half the array. So in this case, we're checking the lower half of the array, and then we just do one timing measurement on the result of the NAND. And that's going to tell us if the cache line's in that half. And then all we have to do is restore the original state of the signal array, which we do using the copy that we didn't use for the NAND. So that's why we had to create 2 copies, one to use, one to restore back. So I tested this out. It works pretty well up to a point. The up to a point is because of the fact that we're using larger and larger NAND gates as we have larger and larger arrays. And speculation is only, we only have so much out of order window in these CPUs. So it works really well up to about 128, then it kind of falls off. It is worth pointing out, this is not fast. We're not trying to optimize necessarily for performance. We're trying to optimize for timing measurements. So the idea is that if you don't have that high precision timer, and you have to do the amplification, it's going to take you a while to do the amplification, then you do want to reduce the amount of timing you have to do in order to improve the performance of your attack. So that's where I could see this sort of technique being useful. The other problem that I want to present here is a cache line counter. And this is sort of the opposite problem. So in this case, we have an array of cache lines. Some of them are present. We don't know how many. We want to find out how many are present. And this could be useful if you're doing, especially a prime and probe type attack, where the victim is going to access a different number of cache lines depending on the code path that they did. And maybe that code path is dependent on a secret value. So in that case, you're just looking to see how many lines they touched. And so we're going to use a counter, but not a normal register-based counter. What we're going to do is we're going to create a counter where the state of the counter is stored in the state of a set of cache lines. So we'll have, say, 6 cache lines we allocate. And if all those cache lines are not present, that means the counter has a value of 0. And each cache line that is present represents a certain bit in the counter. And then we're going to use an adder circuit, this is just your standard half adder, except we have some limitations, because we have limited gadgets and we can only use each value once. We had to make some modifications, but I promise you can, figure it out. It's equivalent to a standard half adder. So we're just going to add each cache line in our input array to the counter by doing these things that manipulate cache line state. So just to kind of walk through what that looks like, initially, they say we flush the cache lines that correspond to the counter from the cache, so they're not present, meaning that the counter is 0. And we'll assume that the left there happens to be our initial array. We'll process the first input, which effectively brings in the cache line corresponding to the first bit of the counter. When we process the second input, that will result in the second cache line corresponding to the counter be brought in, while the first one will become evicted. The third input, nothing changes, except, of course, it gets brought in, part of the processing. And then at the end, of course, we have 2 cache lines that are present, and we just then have to time the access to these 3 cache lines here on the right. We get our counter value. And this one works even better than the other one, mainly because the gadgets here don't have really big fan-in or fan-outs. Everything is just kind of between 1 and 3 inputs. So, yeah, this worked really well in testing, and yeah. All right, so a few takeaways that I want to provide from this. First off, I hope that this sort of is interesting. I think it's a different way of thinking about caches and speculation, and kind of it brings 2 big areas of security research together, where we're using CPU speculation, but not actually to leak data, but to actually optimize how we recover data. So the first thing is disabling high-precision timers is not a very good security mitigation. That's probably obvious at this point. The amplification techniques aren't that hard to do. Also, the results I showed, that was from a single run. So that's where I had one cache line, and I only processed it once. Right? That's assuming that sort of you invoke the victim and you get one shot at it, and that's it. A lot of times in these attacks, you can actually invoke the victim many times, just by calling it again with the same inputs, and you can improve your results that way. If you can call the victim multiple times, then the accuracy is going to skyrocket quickly. I didn't even try that. Monitoring access to timers is a weak mitigation, right? Sometimes there have been techniques proposed to say, well, if you're calling, read TSC too many times, then you're probably doing a side channel attack. We just showed how you don't have to call read TSC, and yet you can still do stuff with cache line state. And then finally, we have this ability to do universal logic gadgets. So we can do things like, binary search, or other kinds of computation that we want to do before we actually need to do any timing. As far as mitigations, I think it's always important to have a discussion about mitigations and anything related to side channels. As far as I'm aware, there hasn't been a lot of focus in this recovery aspect of side channels, and so I think this is, interesting. However, if the attacker is able to get to the recovery stage, then you've already lost, right? That's not the place where you want to be focusing on mitigations. Effective mitigations are going to prevent that execution phase from actually happening, right? Using code that is side channel aware so that it accesses the same number of cache lines in every code path. Or, limiting CPU speculation so that you don't access secret dependent values under speculation. Those are good. Recovery stuff, not so much. And then I'm going to contradict what I just said on the previous slide a little bit, which is that even though disabling access to high-precision timers doesn't work, it doesn't hurt if you don't need them. It's another hoop that the attacker has to jump through, and there is arguably value in that. So, just some ideas for future work here. I started doing this kind of just for fun. I think there's probably more here. There's maybe ways to even amplify stuff further. I kind of ran into that limit where just after about 700,000 iterations, then things kind of degraded. There might be ways of getting around that. I think some more investigation into what caused the signal to get degraded at that point would be interesting. Are there other use cases for some of these things? If you want to go off the deep end, you can even think about what other kinds of computation does it make sense to do with this model where you're not storing values in registers, you're storing them in cache line state, right? Which has this weird phenomenon of if someone touches it, then they effectively destroy the data, right? It's like Schrodinger's cache lines. So, could you use this to maybe detect side channel attacks? I don't know. I've tried to think about if this makes sense, and I haven't come up with a great story around it, but, I think it's kind of an interesting way of hiding what you're doing in your code because it's very non-obvious. And in fact, the data is nowhere in your code. It's all in the state of the cache. So, hopefully this was interesting. Please keep an eye out for the paper from Katzman and their team if you like this stuff. If there are any questions on this, I'd be happy to take some. I think lunch is in like 15 minutes, so I think we have a few. Then. Okay.
Questions? Okay, we have enough time. You'll get to lunch early, but yeah. All right, so I think David will still be around. So yeah, feel free to catch him for a chat. And as promised, the lunch is early. So we'll be back at 2 p.m. And thank you so much, David, for the amazing talk.
Thank you.